It's the sum of 1/2 m sub I v sub I squared this will always work, but it's not particularly useful. So let's make it a little bit more useful. I know that the speed is equal to omega r. If it's a rigid body, everything takes the exact same amount of time to go around. So omega is the same for everything in there. So I'm going to make that substitution here. So this is, well, 1/2 I can just factor out. So I got 1/2 times the sum m sub I omega r sub I squared. I don't have a subscript next to omega because it's the same for everything. R is the distance from the axis of rotation, from the pivot point. So that's going to differ depending upon what the object is. So that's 1/2 times the sum of m sub I omega squared r sub I squared, because I got two things there squaring. I got two things in the parentheses there. I'm squaring each of them. That's a constant, so I can just factor that out. I can just pull that out front. So I'm left with 1/2 omega squared times the sum m sub I r sub I squared. And at this point, you're looking at it going, oh wow, that's incredible. Who thought of that? Did I read your minds correctly? Excellent. This actually is a shortcut, although it might not look like it right now. This is the moment of inertia. Or rotational inertia, whichever way you want to go. All right. So if I have a disk, that's supposed to give some sort of sense of dimensions there. So disk, solid disk. Let's give it a mass of 4 kilograms and give it a radius of 2 meters. And it's rotating at 6 radians per second. What's the kinetic energy? Well, like kinetic energy of this would be 1/2. And that is, there we go, 1/2 I times 6 radians per second squared. What do we do for I? This is supposed to be convenient here, but we're left with this. How do you calculate the moment of inertia? Well, you take the object, you break it up into a whole bunch of little pieces, and you calculate this for. I think for the audience of 1, or anyone who's had calculus, I officially is. But just a side note. All right, so here's why it's convenient. There we go. On page 138 of the textbook. Page 138. There's a table here. As a matter of fact, pretty much every beginning physics textbook which has mechanics in it, so that would be this through 250, 251, are going to have a chart like this. There are certain shapes, somebody's already gone through and done the math for you.
What page is it?
Page 138. They have it for a simple pendulum, which is just basically, I got a string with, who cares, with an incredibly tiny mass and a ball of mass at the end. I got hoop about normal axis. And the normal, as we've talked before, is perpendicular. So let me grab that little hoop. All right. Oh, I've used the wheel. It's one of those days. All right. So I have, so about the normal axis. So if you picture the plane that this is in, normal is perpendicular to it, so rotating about the normal axis is that. Rotating loop, rotating about its diameter is rotating around like that. Then they have a stick about one end, a stick about the center of gravity. So this one has a different moment of inertia than if I'm spinning about here. And then solid cylinder and a solid sphere, rotating about its center of gravity. So the question is, I have a disk here. Which of those shapes would be a disk? I'll read them to you again. The shapes that they have in here: simple pendulum, hoop about normal axis, hoop about diameter, stick about end, stick about center of gravity, solid cylinder, and solid sphere about center of gravity. Yes? What's the difference between a cylinder and a disk? Pretty much in everyday language, yeah. I think most people would call this a disk. They'll say not convinced of that. What would you have called it? Cylinder? Okay. Hawk. In my thinking, I picture that if the height is small compared to the radius, or is less than the radius, I call it a disk. Otherwise, I call it a cylinder. But apparently, some people are more evolved than I am on that. But this isn't, from a physics point of view and from a math point of view, cylinder and disk are the same thing. So all we need is the formula, which is given. So a disk spinning about the center there. The moment of inertia formula, 1/2 mr squared. So 1/2 times 4 kilograms times 2 meters squared, which is 8 what? I'll give you a hint. There's no one word unit for it. Think about what we multiplied here. Are you stopping there?
Meter square.
Yes. It's a kilogram meter squared. They haven't bothered to give it any special one-word name. Therefore, nope, not that. No. Has anybody figured out what I'm doing to make the whole thing move versus? Is there? Is it if I touch it at 2 points? Ah. Ooh, you can shrink it. But I won't touch it at 1 point there.
I guess it depends on the pressure too.
I feel like that was the same. All right, anyway, we're here now. Ignore that. So this is equal to 1/2 times 8 kilogram meters squared times 6 radians per second squared. And we end up with
154.
154?
144.
144. Units?
Joule.
Yes. Now wait a second. A joule. Oh, questions before I do my bit on. There seems to be something wrong, but there actually isn't. Routine. All right. So let's go to that routine. A joule, if I do 1/2 mv squared, formula for kinetic energy, in case you were wondering. My units would be kilograms times meters per second squared, so I got a kilogram meter squared per second squared, which is called a joule. By definition, thus the 3 lines. If I look at what I multiplied over there, I have a kilogram times a kilogram meter squared, and then I multiply times radians squared over a second squared. And I'm saying that's a joule. What about the radians? Can I just ignore radians when it's convenient? Someone take a wild shot at that answer. So let me ask it again. Can I just ignore radians when I feel like it?
Yes. Here you can.
Yes. Yes, you can. Radians is a unitless unit. All right, so where does that come from? How come we can ignore it? Well, here's how. I'm going to erase this. Anybody do anything here?
Oh, what is that at the bottom of the disk really quickly?
That?
Yeah.
It says 6 radians per second.
Okay, that's what I thought it was. Make sure that I had it down.
Anything else? All right. We earlier, actually it's still over there, we had that the speed is equal to omega times r. And formula for speed is change in x over change in time. In omega, the change in the angle over the change in time times r. The time's the same. I can just multiply both sides by that time and it goes away as long as they're, I got a factor, same factor in all in the denominator or all in the numerator. I can cancel it out. So I'm left with this delta x is equal to delta theta times r. So delta theta must be delta x divided by r. Let's take a look at units. What's the unit, standard international unit of theta? Yep, it's a rad. And the unit of distance?
Meter.
And the unit of radius? So radian is a meter per meter. Well, I got the same thing on, what's, any fraction that has, other than 0, the same thing on top and bottom is equal to what?
1.
You can ignore radians whenever you want. You can stick them in whenever you want. A couple of years ago, pre-pandemic, I had a student, a 151 student, or yeah, 151, who decided to put radians at the end of all of his answers. He's not wrong. So why do we bother having a unit there when it's just equal to 1? It's all about communication. If I said, I have a wheel that rotates through 5, and I just left it like that, I think most people would think I meant 5 degrees, and I just forgot to say it. But if I don't put units down, it's supposed to be radians. So I'd say it rotated through 5 radians. That definitely very clear about what I'm saying there. Definitely not 5 degrees. 5 radians would be about rotating from here to something like that. 5 degrees. So sometimes you will see, in that last problem, it was rotating at 6 radians per second. Sometimes they'll just write 6 per second, or for those who've dealt with exponents, I've asked one just a side note. and something that we will get to before it's over, or should be able to get to before it's over. I have angular speed here, angular speed. And omega is the traditional symbol for it. And the units of omega are radians per second. Later on, we will run into something called angular frequency. And the symbol for angular frequency is omega. And the units of angular frequency are radians per second. There's a philosophical difference between the two. I cannot think of any example where it makes a difference whether you call it angular frequency or angular speed. It's usually context which one you use, but if you see one, you can treat it like the other. Questions right here? All right, I know there's been a couple of at least downtime as I went to go find stuff, but why don't we take an official break now? We'll come back renewed, invigorated, and we'll talk about G2 Kabuka. All right, G2 Kabuka. What I have here is a box with stuff in it that I probably should take out before I drop it. And what I want you to do is tell me what I need to do in order to close the lid as efficiently as possible. I assume everyone in here has at least opened or closed a door at some point in your life.